Hi, my name is Gary Kenworthy, and I work at Cryptography Research. We use encryption every day: electronic payments and banking transactions, encrypted storage, premium content protection. These are just a few of the applications in which our mobile phones, PDAs, and tablets use secret cryptographic keys to protect sensitive or secret information. At CRI, we set out to test mobile devices to see how secure these operations might be. We expected to find some leakage, but what surprised us was the extent to which these devices leak. These mobile devices all have radios for wireless communications: cellular, Wi-Fi, Bluetooth, and the like. But these radios are not the sources of the leaks that we're finding. In fact, we put the devices in airplane mode to turn all of the radios off. This unintentional electromagnetic radiation can be picked up using a common radio receiver. By digitizing and analyzing these signals, we can extract and decode the secret keys used in the cryptographic algorithms. Leakage signals can be picked up by a probe that's as simple as a loop of wire that responds to the magnetic field coming from the device. This wire loop is connected to the radio's antenna input. The radio intermediate frequency output is connected through a home-built amplifier to an inexpensive digitizer. We've written our own application that calls standard crypto libraries, and we've installed it on this phone. I'm now going to make it run RSA operations in a loop. On the computer screen, we have several displays. This one shows the radio spectrum centered around the frequency that the radio is tuned to. As I move the probe around the phone, we see energy fluctuations of the magnetic field coming from the phone. When we see an interesting signal, we can tune the frequency and the position of the pickup loop to maximize the signal. We also adjust our bandwidth to give us a better display. Now we look at the signal in the time domain. This is like an oscilloscope. We can begin to see patterns in the signal. Notice the sharp vertical transitions representing sudden increases and decreases in radiated power. The two large power blocks with a short drop in the middle is a characteristic of the Chinese remainder theorem implementation of RSA. Zooming in on the individual operations, we discover even more. In this magnified time view, we again see sharp vertical transitions and varying durations of increased power radiation. We also notice that the duration of each pulse varies. This is the way that the signal that we are seeing reveals the secret bits of the key. The pattern reveals that each 1 in the secret exponent consists of a squaring step followed by a multiplication step, while a 0 in the exponent involves only a squaring step. So, with a single trace, we can directly read each of the secret bits and completely recover the secret key. Secret cryptographic keys can also be recovered from a distance. We will use this antenna connected to the input of our radio receiver. We've written our own application which performs elliptic curve point multiplications, which are part of ECC cryptography. I'm now going to begin those operations in a loop. As the crypto has started, we can actually hear the operations. But it's also interesting that we can hear it and recover the secret key from a distance. The transitions we see here represent the double and add components of the elliptic curve operations. Looking at the plot, we can see that the double takes less time than the add. A double operation by itself represents a 0 bit, and the double operation followed by an add represents a 1. In being able to read this sequence, we can recover the entire secret key.